research scholars. I'm really proud to be here with you this afternoon to attend this 2 days international conference. And for this, I am very much thankful to Professor Pal for inviting me and giving this opportunity. I'm going to talk about one of the most uh, demanding subject today, which is AI and machine learning. Let me start with the famous remark made by great scientist and physicist Galileo. He said that mathematics is the language in which God has written the universe. But in this 21st century, one might say that mathematics is also the language in which machine tries to understand the world. There is no doubt that AI and machine learning is one of the advanced technologies today. But the success of this technology lies behind the subject, which is mathematics. Mathematics, with the help of calculus, linear algebra, probability, statistics, it actually provides the structure. And this structure actually transform the data into knowledge, and then knowledge into intelligence decision making. So I'm going to give you a very brief overview of machine learning. Though I'm not very expert in this subject, but Professor Paul asked me, I have to tell something which is related to AI and machine learning. So I'll give you very basic things of machine learning today. Before I proceed to give you that mathematical foundations of machine learning, I think it is better to understand that where this machine learning actually fits in the broad landscape of artificial intelligence. Artificial intelligence is the broadest field, and this is a technology which enables computer to mimic human behavior. Like if a robot laughs, then we see that this robot is behaving like a human. And machine learning is actually that subset of this artificial intelligence. It is the ability to analyze the data and without that external any instructions. And deep learning is that the subset of this machine learning. And deep learning uses artificial neural network to go more deeper into the data and extract patterns of the data. So as I told you that machine learning is nothing but the science of training a computer system without to perform the task without explicit instructions. How does it work? It actually develops algorithm, and this algorithm is used to analyze the data, to find the pattern, and then we make the prediction. So there are basically three types of machine learning: supervised learning, unsupervised learning, and reinforcement learning. Supervised learning actually uses the labeled data. So a labeled data is a data in which you have input and you have also output. So with this type of labeled data, so you have to train the machine first. And during this training, so machine or algorithm tries to find the relationship between input and output. So after the training, then whenever the new data comes, then the machine is able to find or able to predict that output of the data depending on the relationship it learns. So this is called supervised learning because as if a teacher is supervising the learning process. And we will see that there are two types of supervised learning. One is called classifications. If that output is of say categorical type of values it takes, and otherwise it is called a regression. So we all know what is a regression. So now another type of machine learning is called the supervised unsupervised learning, where this labeled data is not used. That means that You have the input, but you don't have the output. You don't know what will the output. So in this type of data, what machine actually is to do is that it tries to find some groups. It will group some data. It's called cluster, and then that clustering made based on that similarity or difference or pattern of the data. The similar data, similar behavior will be put in one cluster on group, and these clustering can be done in various ways, like density-based clustering, center-based clustering, or probability distribution-based clustering. So this can be done. And another, the third type of category is called reinforcement learning. And in this type of learning, so the agent or decision maker makes decision based on interacting with the environment. When that agent or the decision maker interact with the environment gives some feedback, and in this feedback in the form of reward or penalty, and that agent's objective is to actually maximize that cumulative reward in order to make its decisions. I will come to that more about these techniques of machine learning later on. Now, if I come to the first, the supervised learning, as I told you, that objective is to find the linear relationship between the input and output. So simply, if you have say n data, say x1, y1, x2, y2, xn, yn, then it is a training data. Then you have to find that the function f has, so that fxi is near equal to yi. If yi takes the value, say categorical values, or say natural numbers, then it is nothing but that classifications. This figure shows that there are two classes, class A and class B, and if y takes that real values, then it is the regressions we know. So we'll fit some straight line, it's a linear regressions. Then based on this fitting of the top, we'll predict what will be the output. Now the question is, how can we find this f hat? That is that relationship, the function between x and y, so that your prediction will be nearly equal to this output. That's the main thing. So for this, suppose let us consider input x from the input space, say capital X, and our objective is to find a prediction function from x to capital Y, so that this output will be y, which is belonging to output space. So for this objective is to find the prediction function t, and over the pair of values of this distribution. So one has to find that maximum value of prediction. Maximum value of the prediction can be alternately said that it can maximize that expected value of this indicator function. This indicator function is nothing but whenever this prediction is near equal to your y, this value is 1, otherwise it is 0. So you are going to find you are going to maximize this expected value of this indicator functions, and for this we have to assume that what is that functions. For this you can think of that class of prediction functions, and if this class is very big or very large, or if this class contains diverse complex functions, then it will be difficult to find that functions which satisfies these equations. In other words, if you think of very small class of functions, then also, even if you can get a prediction functions, that may give you a very poor prediction. So you have to be very careful about choosing that classifications of that classifications. That class of prediction functions. Okay, so neither big nor small. So you have to be careful, very careful. Suppose we have assumed the prediction function p such that it is parameterized by the parameter w. So we assume that the prediction functions parameterized by w, and for the linear case, the p can be written like this one: w0 plus w1 into x. So it's a linear case. So then your this equation 1 reduces to this form: maximize this expected value over that parameter W. So you have to find the W so that this X value is maximized. Now, in case of classification, so y value will take say +1 and -1. So it may take 0, 1, etc. value also. If you think of this +1 and -1, then this expression, so Pwx is near equal to y. These expressions can be expressed as yp is greater than 0, because y when is y is positive, p also give the positive value, otherwise it will not be equal. So they are negative, then both will be negative. So yp must be greater than 0. We can assume this. And in case of regressions, this Pwx near equal to y, this simply can represent this fact that norm of y minus Pw is less than equal to delta. So we are considering now, since we know all what is the regression, so I am focusing on these classifications. So in case of these classifications, then we use this expressions yp greater than 0 in this equations. So then our objective is to maximize this one and find the value of W. And the problem can still be written as in the minimization form, because if we change this inequality greater than equal to less than equal to sign, then this is a minimization problem. So whenever you change it into less than equal to sign, this is nothing but it's called the 0-1 loss functions. So using this 0-1 loss functions, you can minimize these objective functions and you can find the value W. But one problem is that this 0-1 minimization function is a discrete functions. So dealing with the discrete functions in optimization is very difficult. Another thing is that this 0-1 loss functions may not is not giving you that magnitude of the error. It is not quantifying the magnitude of the error. This is the problem in this 0-1 loss function. Now, in order to resolve this issue, we may think that this the label is not deterministic. First, it is not deterministic, and we assume that y represents that random variable corresponding to this correct label for x. That is, y is taken as a random variable. So ypwx greater than 0 is equivalent to, we can that the probability of y is taking the value y when x is given, the input is given, and this probability is greater than half. So if likelihood of attaining this probability is greater than 50%, then we assume that this is the correct predictions. Otherwise, it is the wrong predictions. So then you see that this yp belongs to R. That means it takes that value can be minus infinity to plus infinity. But this probability is taking value 0 and 1 only. So then we need some connections between this. For this, instead of using this probability, we consider a logic transformation. So this is the logic function, and yp we assume this logic function. The benefit of assuming this logic function is that if we take that this probability is equal to 0 plus, so then this is left hand side is approaching to minus infinity. And then if you take that probability is equal to half, then this will give you 0. And if it is a some equal to 1, y equal to this probability is equal to 1, then it is giving you plus infinity. So then this yp is taking value from minus infinity to infinity. So for these reasons, we assume this logic function. And after some simplifications, we can get pyx equal to 1 by e to the power minus py. This is nothing but called this logistic functions. So since we are using this logistic function, this is called this logistic regressions. So we are coming to the logistic regressions, and the problem still remains: how can we find the parameter W? So this parameter W is just in this expression, we just change the parameter. Instead of W, we are considering theta. So Px theta is equal to 1 plus e to the power 1 by 1 plus e to the power minus, say, theta 0 plus theta 1 to x. So objective is to find theta 0 and theta 1. This parameter value we have to find. And then these parameters can be used to can be found by using simple, if we assume the probability distributions as this thing is considering as the probability. That means the prediction functions you are considering as the probability. So probability of y equal to 1 and given x equal to x. So if we assume this is as the px theta, then probability of y equal to 0 for given x equal to x is 1 minus probability t. So this shows that this y, this random variable, follows the Bernoulli distributions. If it is a Bernoulli distributions, we can easily find the PMF of the Bernoulli distribution. which is nothing but p to the power y into 1 minus p to the y minus y. So whenever you got this PMF of this Barnum distributions, you can easily find for the given training data, you can easily find that likelihood functions. So you can formulate the likelihood functions, which is nothing but the product of all the probabilities for the data. And then after finding these logistic functions, you can find the likelihood functions. You can easily find that log likelihood because of the simpler computations. So when you know that log likelihood functions, you can maximize this. So and the maximum log likelihood estimator will give you the parameter values. So like this way, you can find that parameter values of your prediction functions. And instead of using this maximum likelihood estimator, one can also use that gradient descent method, because gradient descent method is useful for the minimization problem. So you can use the negative of this log likelihood functions, and then you can apply gradient descent method. So after this training, so how can we predict that what will be the output? We'll simply go to this. This is your prediction functions. You know now the value of theta 0 and theta 1 by using that maximum likelihood estimator or gradient descent method. And then whenever the new data comes, new data means say here x0, and then you find the probability of this one. So if this probability is greater than half, then you will say that y0 will be equal, the label will be equal to 1. This is correct predictions, otherwise it is wrong. So likewise, you can use this logistic regression to classify the data. Okay, now coming to that another type of very popular classifications tool, which is called support vector machine. And it is that in this logistic regression case, we find the probability whether the probability is greater than half or less than half. If the probability is greater than half, means it is true, otherwise it is false. So consider that whether how these data are distance apart from the decision boundaries. But this issue is considered in support vector machine. So in the support vector machines, we actually find that some margins between the data, and we actually optimize the margin. And suppose first we consider separable training data. So this issue, the red ball and blue balls, they can be separated. That's why it is a separable data. And for this data, we can separate this data by a hyperplane. So this equation hyperplane is wx plus b equal to 0. Now the question is, since between these two data sets groups, since infinite number of hyperplanes you can draw, then which will give you that optimum hyperplane, that you have to decide. So now for this, as I told you, that we will consider this margin between this data. So if this is your hyperplane, then we consider that the nearest data points from this hyperplane, there may be more than one nearest data points from this hyperplane. And from this side, for the red balls and for the blue balls also, we find that the nearest data point from this hyperplane. And if we consider the hyperplanes through these data points, which are nearest to this hyperplane, which are called marginal hyperplanes. So we have two marginal hyperplanes, and these equations of these two marginal hyperplanes, without any loss of generality, we can take wx plus b is equal to 1 and wx plus b is less than 1. Because this is wx plus b equal to 0, so one side will be w, the other side will be wx plus b greater than 0, and other side will be wx plus b less than 0. So instead of greater than 0 and less than 0, we consider that wx plus b equal to 1 and wx plus b equal to minus 1. So without any loss of generality, we can assume this one. So you know the equations of this marginal hyperplane. And if you know the equations of this marginal hyperplane, then easily you can take the difference, and we can find that x2 minus x1 is 2 by actually norm w. So 2 by norm w is nothing but the margin. We find the margin. This is the margin, and your objective is to maximize this margin. So you have to find the w and b. so that you can maximize this 2 by norm W. This is the margin, and it's satisfying this condition. So this y value should be equal to 1 if this is greater than 1, and is minus 1 if wx plus b is less than or equal to minus 1. So you have to satisfy these conditions. You know that these two conditions can be combined into a single equations conditions like this one. So your objective is to maximize this margin and subject to these conditions. So these two conditions can be combined into one. So in into w xn plus b is greater than or equal to 1. So you have to satisfy this condition. So this problem can be equivalently said as minimization problem. So minimize 1 by 2 into norm w, satisfying this constant. So you show that this constant is greater than or equal to 1. So if there's some data satisfies this constants with equality 1, then we say that this is the support vectors. That's why this process is called support vector machines, because we consider this marginal hyperplanes, and that the data which satisfies this marginal hyperplanes, they are called support vectors. That's why the method's name is support vector machine. Now, initially we consider this separable data. So if it is a separable data, you can find that hyperplane in between. But sometimes data are not separable. So you see that the red ball and white balls, this the difference that data are not separable. You cannot draw a hyperplane separating these two. So in this case, the equation changes like this one. So minimize of half norm W plus C into sigma epsilon n, where epsilon is nothing but the degree of classification error. We can say that this is the degree of classification error. And the important thing is that if xi n equal to 0, this classification equal to 0 means that point is on the margin. So like this one, you see that the points are on the margin when xi n equal to 0. And if xi n is less than 1, then this point is inside the margin, on the same side but inside the margin. And if the xi n is greater than 1, then that the points are on the other side of the wrong side of the margin. So this is the three things you have to consider: xi n equal to 0, xi n less than 1, or xi n greater than 1. So this is xi n, the misclassification, degree of misclassification. And C is a parameter which we call it a regularization parameter. So regularization parameter has some important role because it makes the trade-off between the maximizing the margin and minimizing that classification error. So if C is very large, then the model actually averts some misclassification error. If the C is very small, then it can allow some misclassification error also. So the supervised learning can be used for non-separable data also. So now I'll want to show you some very simple applications for the supervised learning. So think of considering these cancer cell detections from the medical images by using the supervised learning. So these are the cells. You see the right-hand side is a malignant tumor, and this left-hand side is a benign tumor. So malignant tumor, if you see that this tumor spreads or invades in some other cells also. So, but it is remain as such, is confined. I'll show you some next slides, good pictures. And now this cells, this malignant tumor cells and this benign tumor, they have some pictures like this. So growth rate is slow for this malignant, benign, and malignant it is rapid or very high. Growth rate will be very high. And then a space locally, but for this malignant, there is space to other organs also. And cell structure is normal, this is abnormal. So I am going to show you this clear picture. So this is that benign tumor, and the structure is like normal, well-defined border. And in case of this malignant, you see that the structure or that is irregular. And this actually spreads or invades to other cells also for the cancerous cells. So this has the property of this malignant tumor, malignant tissues. So now our problem is to classify whether a given cell from this image of the cells, whether we can identify whether it is a malignant or cancerous cells or say non-cancerous cells by using supervised learning. So for this, we need to consider some features. We consider some radius, we consider texture, we consider area. So the radius is more means it is cancerous. And the texture is irregular means, as I told you, this is also cancerous, you can say. And the area will be larger means this is a doubtful case for the cancer. So these are the features we can consider for the supervised learning. And so mathematically, we can say that xi is the feature vector, and this vector has three components. One is radius, texture, and area. And our goal is to learn f, or to learn the relationship between xi and yi. So how can we learn? Let's see. And these are the data. These are training data. That means you know this input and output. These are the features for data one. The features are these x1, x2, and x3. And you know this is for these features. You know this is coming from the cancerous cells. So like this, you got the 10 data, and you know the outcome. So all these features you know, and their outcome you know, whether it is cancer or non-cancerous cells. And so now the model you will do here is the logistic regressions will use. You know the logistic regression is this one. So one p probability of y equal to 1 given x equal to this one. 1 by 1 plus e to the minus beta 0 plus beta 1 x1 plus beta 2 x2 plus beta 3 x3. So your objective is to find the parameter values beta 0, beta 1, beta 2, beta 3. How can we find this value? So in the prediction rules, we know that this y value will be equal to 1 if probability is greater than half. Is 0 otherwise. So this is the prediction rule. For this, you need to find the parameter values. That's why you consider this likelihood functions. L, you calculate this likelihood functions and then log likelihood functions. And then we can use this gradient-based methods to find the values of these parameters, beta 0, beta 1, beta 2, and beta 3. So with some calculations, we find with this training data, using this training data, we find that this z value is this one. So we can find this z value. So after finding this z value, you can check whether how this estimation is giving you good results or bad. So first you try with this z value or the first sample. With the first sample, if you find the z value, you are getting 3, and probability of then the probability you calculate this is giving you 0.95. So as I told you, the probability is greater than half means 0.5 means it is cancerous. So your prediction will be equal to 1. And you see that for this first sample, you are getting that your prediction is correct because that actual is 1 and prediction is 1, so it is correct. Similarly, you can check all that samples. You put in the z value and you put in the values of beta 0, beta 1, beta 2, beta 3, etc. And then find a probability and check. We check that this so this z is actually working well. So then you come to the new data. So if you come to new sample with values of x1 and x2 and x3, and they calculate the z value and the probability, and see that probability is equal to 0.47, so it is in borderline case, you can say. So, and for the second sample, so the x1, x2, x3 values, and find the z value and t is 0.99. So it's absolutely it is a malignant case, you can say. So using this logistic regressions and the supervised learning technique, you can from the image of that cells or tissues, you can predict whether the cell is cancerous or not. Now I'm coming to unsupervised learning. Unsupervised learning, as I told you that you will be given that input only, no output. So you have to find the function f, which actually maps from x to z. Z is nothing but a meaningful structure or pattern or a clustering of it. So you have to find this Z, and this Z can be, as I told you, that can be done by clustering. So one of the popular clustering techniques called K-means clustering. That means this K-means clustering is actually based on centroid. Centroid-based clustering, as I told you that the K-means means there will be K clusters. So you have to make K clusters of the given data, and means here means you have to consider the centroid of the, depending on the centroid of the cluster. So your objective is to minimize within the cluster some of the square distances from each point to the assigned centroid. So mathematically we have to minimize this one. This is nothing but the objective is to minimize the variance for each clusters. So if you can minimize the variance of each cluster, here K clusters, then you can make K clusters. You see that like this, you can get the centroid is here, and all these data are nearest to this center, and this data is not nearest to this center, this data is nearest to this center, all this data is nearest to this center and this center. So you can here the picture shows that all the data are nearest to their respective centers. So here the k clusters means there will have k centers, so data will be nearer to that k centers or centroids, what we can say. So this can be explained by taking a simple example. Say, suppose you have 5 data points. So in 2D space, you want to make 2 clusters, or say cluster 1 and cluster 2. So arbitrarily you put 3 data in cluster 1, the red balls in cluster 1, and white balls in cluster 2, arbitrarily. So now, by using this k-means clustering, what you have to do that for these 2 clusters, first cluster 1 is 3 balls, and for these 3 balls, you first find that centroid of this 3 data. So centroid is shown by this red cross. So the 3 red balls center is in red cross, and then 2 white balls, the center is in white cross. So after finding these centers, you then again you reassign each point to this closest cluster centroid. That means you think of these centers and then check the distance of this point from this centroid and from this centroid. Okay. So if you find that this point is closer to this one, you keep you keep this point to the cluster. In this center is this one. If you find that this point is nearest to this one, then you keep this point to that second cluster. But the figure shows that the red point is nearest to this white centroid, but the red point is farthest from this red centroid. So according to the rule, then this red points should be in the white clusters, white center cluster. That's why you put it in the white color now. That means this point is belonging to now the second cluster. So this is the first cluster, this is the second cluster. And then this process continues until there is no switching off of the data. So you see that ultimately we will get this one. So these 2 red balls and this is the centroid, and these 3 white balls is the centroid. So and since there is no overlapping in 2 successive steps, then we can stop. So you can get 2 clusters. So now I'm coming to the third type of machine learning, which is called the reinforcement learning. As I told that this reinforcement learning has 4 components. One is agent, another is the environment, one is the actions and rewards. So agent is the decision maker. So if the agent is in some state, say ST, it can take some actions AT, and for this action, the environment gives some return. Okay. So and this for this return means the reward or penalty. And again, for this actions, the environment will be changed, that the state will be changed, and then agent will again take some actions. Likewise, this process will continue. So you see that perfect example of reinforcement learning is dog training case. So you see that trainer is the environment, and the agent is the dog. So it's the decision maker. So trainer is giving some instructions, and the dog is following these instructions and taking some actions. Suppose trainer is asking to sit, and what that dog will do? It will follow, it will sit or it will stand. So it will take some actions, and depending on the actions, if it satisfies the trainer, then it will give some reward. Okay, trainer will give some reward to the dog, like some food or some toys, etc. If it is not, then he will not. Trainer will not give anything. But initially, that this trainer will give some instructions, then dog may not follow all the instructions. But after some time, you'll see that since for the correct response, since dog is getting some food or some toys or some reward, so dog will learn what to for some specific instruction what to do. That means after this training period, dog will learn the internal in that dog's brain, that some mechanism will develop, and then after the training, when the instruction tells something, dog exactly follows this thing. So actually this is a perfect example of reinforced learning. So depending on that reward it is getting, and the dog tries to accumulate the maximize the reward. So dog is giving taking that actions which satisfies this trainer. So what is the difficulties is if it is the process, the difficulty is that in every step of learning, it is very difficult to know which action will actually give you that better data. It is, you cannot tell which actions you will take so that you will get the better data. So what, for that you have to do some trial and error. You will do the some trial and error, and then based on this trial you will get some reward or penalty, and then if you accumulate this one and maximize this one, it will determine which actions you will take in that on that stage. This is that basic principles of reinforcement learning. So now I'm coming to that mathematical framework of reinforcement learning. Suppose the environment consists of some states denoted by this S. State S is denotes the states of that environment, and agent, which is the learner, it takes up actions. Action state, the set of actions is A, and it receives some reward. So reward can be considered as a function, and it depends on that action you take and the state in which you are. So reward is a real value, but depends on that state in which you are and what actions you are going to take. So because of these actions, there is a change of state. The state will change. It may be deterministic change of state, or it may be probabilistic change of state. So deterministic change of state means the new state will depend on which state you are now and which actions you are taking. And the probabilistic change of state means if you are in state S and taking the action A, what is the probability or likelihood that you will be changed into that state S dash? So this is the probabilistic change of state. And policy is nothing but the actions you are taking, which actions you are taking in while you are in state S. And value of a given policy is nothing but that it's a real value is giving you that accumulated rewards you are getting while you are in state S. So now see that suppose you are in state ST and you are going to take the action AT, and for this action state changes to ST plus 1, and environment is giving you some reward RT plus 1. So again, while you are in state ST plus 1, you are going to take some actions AT plus 1 say, and state changes to ST plus 2 and you are getting the reward RT plus 2. So this is a infinite Haugen model, you can say, and the value of this state is nothing but the expected value of this reward. So expected value of RT plus 1, RT plus 2, RT plus 3 and so on. So why we are considering the expected value? Because some actions can be taken in probabilistic term. That's why we will take the expected value. But the thing is that if you consider these expressions as the correct expressions, then you may end up with an infinite reward. So R plus, you are adding these things, you may end up with an infinite reward, which is physically not possible. So you are not getting that infinite reward. So that's why for this mathematical reasoning, we can introduce some parameters. We call it gamma for the second term and gamma square in the third term and so on. So this gamma is called the discounting factors. So it's lying between 0 and 1, and this then will give you the value of the state as these expressions. This is nothing but the expected value. This is nothing but the accumulated value, all the expected rewards. So you are getting here, and then this is your optimal maximum value, maximum reward you are getting. That is the maximum value you are getting, and that maximum value, for that maximum value, what actions you are taking, that is your optimal policy. So say you are in state say S0, and V star S0 is maximum of this cumulative rewards, and for all the sequence of actions you are taking from A0, A1 to etc. So this can be written in this form. So first, suppose you are taking the action A0 and the immediate reward is this one, and then gamma into max of this remaining part of this expressions can be written as gamma into maximum of all the actions you are taking after the first one. So that way is equal to 1 to infinity, and this one. So these expressions can be written as maximum of A0 if A0 is 0 and plus gamma into V star H1. So this is nothing but the decomposition principle optimal policy, which is very near to that Bellman's principle of optimality. So in the Bellman's principle of optimality, the optimal policy has the property that whatever the initial state and actions, this is the initial state and actions, whatever the initial state and actions, the remaining decisions, so remaining decisions will give you an optimal policy depending on the actions you are taking, and for this state you are changing to that state. So this is nothing but the Bellman's principle. So what we are seeing here, that the reinforcement learning, behind this reinforcement learning, there is nothing but the optimization techniques of dynamic programming. That is Bellman's principle is applied here. So now coming to this deep learning, which is uh, uh, deep learning in the sense that we have seen that supervised, unsupervised, reinforced learning, and this deep learning actually works based on these biological neurons, so influenced by the biological neurons, and these biological neurons receives inputs or signals and process the data and give some outputs, and these outputs again works for the input for that next neuron. So this neuron actually receives signal to and from the other neurons, and they together form a network. So this is the structure of network. For the input and between the input and output, there may be some other layers also. We call this a hidden layer of this neural network. And the thing is that mathematically, a neuron can perform actually perform this affine transformations. Affine transformation by this nonlinear functions sigma. That means the output signal will be equal to that sigma into x plus b, where x is the input signal, x is the a is the, it represent the weight vectors, and b is the bias, and sigma is the activation functions. So activation function is the heart of this artificial neural network. And there are several activation functions like Heaviside activation step functions. For any input, it is giving two values, 1 and 0, and these outputs are used for this binary decisions. There is another activation function called sigmoid activation function. So for any input, it can give that probability value between 0 and 1. And the most widely used activation function is a rectified linear unit. And this is most widely because the computational is very efficient. These are the graphs for this, all these activation functions are shown. And for each activation functions has their individual benefit or individual merits, but that the main objective or common purpose of all these activation function is that to introduce the non-linearity in the network model. So without activation functions, then if you consider this only affine transformations, then we'll end up with a single linear linear model, because if you put y is equal to here, you will get see that ultimately you will get the linear model. So if you use that activation functions, then the non-linearity comes. This is a perceptions. It's nothing but this is simplest form for simplest type of artificial neural network. It has some inputs, and these inputs are multiplied by the weights W1, W2, Wn. Then they are sum up and adding some bias, and then if we apply some activation functions, we'll get some results. But this, since is a simplest one, so this is basically used for this binary classification. So here you use that Heaviside function, so we are getting only one input, one output. But in reality, we may have several outputs. We may get several outputs. But using these perceptions, we can get several outputs for different sets of weights. If you have different sets of weights, then the bias also. So for this one set of weights and bias can be used for to get y1, and for other set of weights and bias, we can get other output. Not only this simple multi-output perception, we may have also hidden layers. Same thing we can apply. For this part, we have one set of weights and bias, and then for this part, we have another set of weights and bias. And then you can get, if you have a hidden layer, one hidden layer, then you can get also, in the same way, you can get the two outputs. And not only one, not only one hidden layer, you may have several hidden layers. And the same technique we can apply that affine transformation, activation, affine transformation, activation like this compositely, and then you can get the output, different outputs. Here you see that two terms are used: that depth of this neuron, depth of this artificial neural network, and width. Depth is nothing but how many hidden layers are there, or sometimes total number of layers, we call it as that depth. And this width is nothing but in any layer, how many neurons are there. So in this layer, this 3 is that width, and this is that 5 is that width of this layer. So if you use the more width in any layer, so that means you are considering more features for this complex um, uh, uh, data or accurate predictions. You can use this one. And I will close with this example. Suppose you have some data is given and for the students data. So how many classes, how many hours the students is attending the class, and how many hours the students is using for the final projects. So this is that results. You see that green means they pass their exam, and this red means they fail, because they use very less hours for their study, and also there's less hours for this project work. So all these are green means they use sufficient hours for the study and sufficient hours for the project. Now, if you want to use this data for this neural network, then what will happen? Suppose you have two inputs and 4 and 5, and if you arbitrarily choose some weights and bias, then ultimately you use some activation functions, say heavy-side activation functions, then you will get some results which is 0.1 something is a probability, and that means that what actually is happening. So that means this is the student. So this is the student. This graph shows that he passed the exam, but this neural network is giving his failed the exam. So that means that the neural network totally fails. What is the reason? The reason is nothing. The reason is that you never train the machine. You never train the neural network. So for this, you have to find that what is the empirical loss for this training data. You have to first find the empirical loss for this training data, entire data. So this is that empirical loss expressions, and loss is nothing but the difference between the correct and the predicted value. And then your objective is to find that W by minimizing this empirical loss function. So that you can do by using gradient descent method. So you use the gradient. If you use the gradient descent method, then you have to consider all this entire data, and your the updates will be like this: W equal to W minus theta into this gradient. Theta is nothing but the learning parameter. And this gradient can be calculated by using the back propagations. Using the chain rules, we can use, you can find this gradient. But anything is that in order to simplify it, we can use, instead of gradient, we can use the gradient distance. That means here is whole data. Instead of whole data, you can use a sample of data. So then the computation will be less. And even the simpler form is that the stochastic gradient method. So in the stochastic gradient method, you will arbitrarily consider one data. But the difference is that this Bayes gradient is better than the gradient, and stochastic gradient is better than the Bayes gradient. And you see the data used for update is entire data on entire batch, and here only one. And the speed is slow, and obviously it will be fast because only one data you are considering. And convergence is noisy for this stochastic gradient, and for this one is smooth. So with this, you have to choose which process you will consider to find that optimal value of your parameters. Then you will take the decision. Now, since there is no time, we just quickly conclude this talk. That the machine learning is fundamentally a mathematical discipline. It is not just that the collection of algorithms, and whatever you do, like logistic regressions or support vector machines, or say artificial neural network, deep learning, whatever. So mathematics is there, and without mathematics we cannot optimize that technique behind this. And this linear algebra, calculus, probability, and optimal theory, that these are used to make that intelligent decision. So as a whole, I can say that mathematics is not just supporting machine learning. It is actually what I can say, that it is the language of machine learning, in which the machine learns, adapt, and make intelligent decisions. With this, thank you so much for your patience. Because of shortage of time, I have to be very quickly explain. Otherwise, it will be better to explain slowly so that the students can learn better. So thank you so much for your presence.
Thank you, Professor Giri, for your excellent talk. But due to the shortage of time, we are not given more time to you. So, any question? We can take one or two questions from the audience. So, you can ask during the lunch time. Okay. So, I congratulate and thankful to you. So, you certificate. Congratulate for this certificate. Actually. Okay.
Thank you. I was so fast that whether the students will be follow or not, I don't know because of
So
time.
thank you, sir. Although you are saying it's very fast, but I understood it very rigorous and compact. So it's very nice, and we are thankful to you. And as a gesture, we are also providing you with a Research Excellence Award certificate, and that certificate will be handed over to you by Professor Pal. Sir, please.